Chapter 2. Einstein's reification of the semi-Riemannian manifold. In this chapter, we examine Einstein's reification of the semi-Riemannian manifold. We begin by asking why the specific mathematical structure known as a manifold, and what is that structure? So we begin with some definitions. Further math background on differential geometry, differential topology, and algebraic topology has been placed in the appendix. 2.1 Why manifold? Chaos universality, Morse theory, and Palet. Geometry is a manifold, not a field. Indirectly, it is a manifold defined by a set of fields satisfying local Lorentz invariance. Thus it will satisfy Lorentz invariance locally, as well. See Book 2 for details. If classical field invariances imprint on what we are calling the physical manifold, that we simply call the geometry of the system, what else imprints on the definition of physical manifold from the classical theory? Most notable in this regard is the classical behavior known as chaos, which is clearly exhibited in terms of simple classical trajectories in Book 1, but also is seen in fluid dynamic systems and fields in general. Thus it presents a seemingly strict constraint or imprint on the behavior of the manifold. Surprisingly, rather than restrict to a subclass of manifolds, the imprint of the chaos universality constraint selects the mathematical object of the manifold itself.
Consider the scenario where the system description is maximal in the sense that it includes all behavior, trajectories, up to the edge of chaos. Such limits are considered in situations where evaluating the maximum allowable noise perturbation/transmission the system can sustain, such as in Book 7. What this would indicate is another type of local behavior other than Lorentz invariance, here known as chaos universality. This is because, from chaos theory, there have emerged universal constants, with system behavior describing a path to chaos via period doubling, and central to the derivation of the universality property, that is observed, is the requirement of local quadratic structure. A seemingly benign constraint, described as such by Feigenbaum, but if taken to be a strict mathematical property of the system, thus not a universal output of the system description for instances of explicit chaos, but a universal input to the system description, then from algebraic topology, appendix, we arrive at the requirement that it be a manifold structure. This is because local quadratic structure, as indicated, is by Morse theory, and the Palet lemma, indicative of a manifold structure.
So, geometry is a manifold, not a field. Of course, all are present in a physical situation. Geometry and field and matter, which can be represented as a spinor field at the elementary level. From the Witten positive energy theorem, this imposes a constraint on the manifold and field such that the WEC is satisfied, or AWEC for QFT. The WEC, in turn, must be satisfied to not have CTCs, as explored in Chapter 7. WEC is thus a given if we are seeking the maximal system representation that be functionally described. Thus, we can posit any kind of field locally, but we cannot do the same for the physical manifold consisting of manifold with field. This means the manifold is constrained positive energy, in a way that the quantizable fields are not.
Geometry, as manifold, and standard model force fields are found to couple to matter very differently. Take the classic electromagnetic field coupling to matter represented by alpha, versus the gravitational coupling given by the gravitational constant g. Alpha is dimensionless, while g has dimension. This alone destroyed the possibility of the gravitational theory having a renormalizable quantum field theory due to the proliferation of infinities at all orders in the dimensionful coupling constant. Various orders of alpha, on the other hand, are just numbers, dimensionless, and can be added, to only have one infinity, for example, to offset via renormalization. So, physical geometry is only consistently described via the mathematical object of a manifold. The manifold with matter field is constrained as mentioned above, but what of constraints when just considering the manifold itself? The most significant of these will result from the simple observation that rigid bodies don't change length on rotation, e.g., exist. This will result in the requirement that the manifold have a Riemann metric.
2.2 Why the Riemannian metric? Notes in this section make use of notation and examples from, including the use of concrete index notation, abstract index notation, by Penrose, is described in the appendix. In studying surfaces in three-dimensional Euclidean space, Gauss introduced a general parametric representation of surfaces, U sub 1, U sub 2, where intrinsic geometric features are expressed independent of surface coordinates, including distance as, see equation 2-1. In 1854, Riemann publishes, On the Hypotheses Which Lie at the Foundation of Geometry. Riemann points out the restriction of Gauss to the case of two surface coordinates was not necessary and only motivated by his focus on two-dimensional surfaces in a three-dimensional space. Riemann proposed the n-dimensional, but still quadratic generalization.
See equation 2-2. The quadratic form is a function of the du sub I prime s, e.g. ds equals f of du sub I, but more general would be not just quadratic and also have explicit coordinate dependencies. ds equals f of u sub I, du sub I. Such general spaces are known as Finsler spaces. It was pointed out by the famous mathematician Helmholtz, however, that most Finsler geometries can be excluded since they lack symmetries. In fact, the simple existence of systems where we rotate a rigid body about a fixed point require transformations to exist that are length-preserving. We will now show, following a discussion from, that requiring distance-preserving transformations to exist requires the geometry to be Riemannian.
We assume a metric function exists in which three-parameter groups of distance-preserving transformation are possible for a rigid body. Suppose near a fixed point O we have ds equals f of dx sub I. Introduce a local coordinate system around the origin O. We have a three-parameter family of transformations x sub I equals f sub I of x sub k, p sub j, which depends on the three parameters p sub j. See equation 2-3. And now f of dx sub I equals f of dx sub I. So, to begin, consider, see equation 2-4.
Given an arbitrary plane in the E-space, there exists still a one-parameter subgroup of those transformations which carries the plane into itself. Assume epsilon sub 3 equals 0, no loss of generality. Since epsilon sub I equals the sum from k equals 1 to 3 of alpha sub I k of p sub 1, p sub 2, p sub 3, epsilon sub k, we must have alpha sub 31 of p sub 1, p sub 2, p sub 3 equals 0 times and alpha sub 32 of p sub 1, p sub 2, p sub 3 equals 0. Thus p sub 2 times and times p sub 3 can be determined as functions of the remaining free parameter p equals p sub 1. We consider only f of epsilon sub I positive definite. Now, with epsilon sub 3 equals 0. See equation 2-5.
Let f of epsilon sub 1, epsilon sub 2, 0 equals normal phi of epsilon sub 1, epsilon sub 2, 0, and so normal phi of epsilon sub I equals normal phi of epsilon sub I. We can assume without loss of generality that p equals 0 corresponds to the identity transformation and that the matrices depend differentiably upon the parameter p. See equation 2-6, where c sub ik is the derivative matrix of alpha sub ik at p equals 0. Now differentiate normal phi of epsilon sub I equals normal phi of epsilon sub I with respect to p and put p equals 0 to find the identity, also dropping tildes. Define the characteristic curve epsilon sub I of t by the fraction with numerator partial differential epsilon sub I and denominator partial differential t equals the sum from k equals 1 to 2 of c sub ik epsilon sub k, I equals 1, 2. Then,
see equation 2-7. Let m equals min of normal phi, m equals max of normal phi times on times epsilon sub 1 squared plus epsilon sub 2 squared equals 1. Because of the homogeneity of normal phi, we can assert that. See the next equation. Thus, the curve normal phi equals a must be between the circles a/m and a/m, and is thereby bounded away from both 0 and infinity. The general solution to the fraction with numerator partial differential epsilon sub I and denominator partial differential t equals the sum from k equals 1 to 2 of c sub ik epsilon sub k, I equals 1, 2 is.
See the equation shown, with the determinant of the metric of c sub ik minus lambda delta sub ik equals 0, etc. Thus, epsilon sub I equals a sub I cosine lambda t plus b sub I sine lambda t, where the integral curve is an ellipse. Instead of the parametrized form we have. See equation 2-8. Since epsilon sub 3 equals 0 was arbitrary we have. See equation 2-9.
Thus, normal ds squared equals the sum from 2 of g sub ik of normal dx to the ith power normal dx to the k power, and the geometry is indeed Riemannian. Since normal ds squared must be quadratic in the space differentials if the time coordinate differential dt equals 0, we expect that normal ds squared will be quadratic as a space-time differential as well. The only new feature of the extended space-time geometry will be the fact that normal ds squared need not be positive definite.
2.34D tensor analysis transformations at a point, concrete indices. Using Adler definitions and notation to establish conventions for concrete indices. 2.3.14D tensors. Consider, as shown in the next equation, we shall deal with a Riemann space with a metric normal ds squared equals the sum from ik to of g sub ik of normal dx to the ith power dx. We assume g sub ik equals g sub ki and has the signature plus 1, minus 1, minus 1, minus 1. Scalar quantities. Normal ds squared equals the sum from ik to of g sub ik of normal dx to the ith power normal dx to the k power has to keep the same numerical value under an arbitrary change of coordinates since it is a scalar. A scalar field is a point function in the space considered invariant under transformation. Contravariant vectors. Defined analogous to distance differential vector. So, for x bar to the jth power and x to the k power are basis vectors in whatever coordinate system we have.
See equation 2-10. Any set of four quantities the ith power of epsilon of I equals 0, 1, 2, 3, which transform according to epsilon bar to the ith power equals the sum from j equals 0 to 3 of the fraction with numerator partial differential x bar to the ith power and denominator partial differential x to the jth power epsilon to the ith power forms a contravariant vector. Covariant vectors. Consider a scalar field phi. Consider rho the four quantities a sub I equals partial differential phi divided by partial differential x to the ith power transform under a change of coordinate system from x to the ith power to x bar to the ith power.
See equation 2-11. And we have see equation 2-12, where the latter form of transformation defines a covariant vector. Tensors. Once we have scalars and covariant and contravariant vectors, we have the building blocks for more general transformational objects, rank n covariant and m contravariant, known as tensors. See the next equation.
For contravariant vectors, indices above. See the equation shown. For covariant vectors, indices below. The inner product of a covariant vector and a contravariant vector is a scalar invariant. See equation 2-13. Consider a multilinear form P where summation is implied on indices that match when one is covariant and one contravariant known as a contraction. The implied summation is also known as Einstein convention. See equation 2-14.
Where T sub j sub 1, j sub 2 j sub b raised to the I sub 1 I sub 2. I sub a power is a set of n raised to the a plus b power elements, with overall rank a plus b, if a tensor. T is a tensor if, for an arbitrary change of coordinates under epsilon times and times eta, T transforms such that P remains unchanged, a scalar. Thus, a tensor of rank 0 is a scalar, and of rank 1 is either a contravariant or covariant vector. The metric G sub ik is a second-rank covariant tensor. General transformation law of a tensor. See equation 2-15.
So, see equation 2-16. Or, see equation 2-17. A typical example. See equation 2-18.
2.3.2 Tensor algebra. Let's now consider some basic properties of tensor algebra. Equality. A and B are equal if a sub gamma raised to the alpha beta power equals B sub gamma raised to the alpha beta power. Additive property. Sum of two tensors with the same number of respective indices is simply. See equation 2-19, which is a new tensor. Multiplicative property. The product of a tensor by a scalar is again a tensor. The product of tensors is a tensor. The tensor product t sub gamma raised to the alpha beta power s raised to the mu v power equals g sub gamma raised to the alpha beta mu v power is often called the outer product of the two tensors t and s. The reverse can be done, where decomposition of a tensor into a sum of vector products is done, tensor products of tensors of rank 1.
Contraction of indices. T sub j sub 1 comma j sub 2 dot j sub b minus 1 sigma raised to the I sub 1 I sub 2 dot I sub a minus 1 sigma power is a tensor of rank a plus b minus 2, which one can denote a sub j sub 1 comma j sub 2 dot j sub b minus 1 raised to the I sub 1 I sub 2 dot I sub a minus 1 power. The quotient theorem. S equals Ta is valid if the indices count is correct. Then if any two are tensors, the third must be as well. Lowering and raising indices, associated tensors. Consider. See equation 2-20.
The second-rank tensor g sub ik which we are using to lower indices can be chosen arbitrarily. However, once selected, it plays a central role in tensor calculus since it establishes a relation between contravariant and covariant tensors. It is called the fundamental tensor. In a metric space, such as the four-dimensional space of general relativity, it is quite natural to take for g sub ik to be the metric tensor itself. Thus, see equation 2-21. Connection with vector calculus in Euclidean space. Contravariant vector with components, mu to the first power comma mu squared, times u equals mu to the first power e sub 1 plus mu squared e sub 2. Covariant vector with components, mu sub 1 comma mu sub 2, times mu sub 1 equals u bullet e sub 1 comma mu sub 2 equals u bullet e sub 2.
Connection between bilinear forms and tensor calculus. Let x bar sub k equals the sum from I2 of a sub ki x sub I and y bar sub k equals the sum from I2 of b sub ki y sub I, and consider the bilinear forms. F equals the sum from I2 of x sub I y sub I and f bar equals the sum from k2 of x bar sub k y bar sub k. As shown in the next equation. Where? See the next equation. Using the transpose notation, if a to the t power is the transpose of a sub ik, then it is the matrix with a sub ki. We have our condition to be.
See the equation shown. So we have, as shown in the next equation, the contragradients relationship is an automorphism, i.e., it preserves the law of multiplication with the order of the factors. If, for example, a equals b to the t power to the negative 1 power and d equals e to the t power to the negative 1 power, then ad equals open bracket be to the t power close bracket to the negative 1 power.